I am so excited that I wrote my own complex analysis notes and I wanted to share some of the details with you. This was for a course that runs 7 weeks and meets 2 times every week for 2 hours. That's the typical way that courses run here in uh, Finland, I guess, at least in Jyväskylä. So this was a follow-up to Complex Analysis 1 course where students already have seen the definition of complex differentiable functions, Cauchy-Riemann equations, the winding number, the local convex domain version of Cauchy's integral theorem, and a few more things. For example, Liouville's theorem that bounded analytic complex differentiable functions are constant. So I had some freedom and I used it generously to come up with my own syllabus basically. So I put a lot of thinking into this and I considered my own relationship with complex analysis from my undergraduate years, and here is what I came up with. The first thing I wanted to really help students understand was the essence of complex differentiable functions. Because they are so different and it's in every textbook and it's advertised everywhere that they have unique, strange, weird, unexpected, surprising, elegant behavior. But I think there was, at least to me, some missing link, some missing question. But why? But why do they behave so differently from smooth C-infinity functions? And my first goal in this lecture was to get that answer to them. And to me, the answer is hidden in linear algebra, really, in the conformality property of complex differentiable functions. So I don't want to start the lecture. So let me show you what I mean by that. So here's a list of properties of complex differentiable functions. For example, that they are infinitely many times differentiable, although in the definition, as with the, say, functions R1 to R1, we just require once differentiability. Not only that, the stronger property that their Taylor series converges to the function. Then the Cauchy integral formula gives the value of a function and its derivative in terms of the values along the boundary by integrating. The maximum principle that modulus of the function never attains the maximum in the interior unless it's a constant function. There is this property that every open set is sent to an open set. I don't know if you're familiar with that. Maybe it's not universally taught in every complex analysis course. There is no real valued complex differentiable functions, which means there is no analog of simply taking f of xy to say x and 0, because this as a function from R2 to R2 is perfectly smooth. It's infinity derivatives. It's a linear function, so derivative is itself, but it can never be a complex differentiable, which I call homomorphic functions. And as I mentioned, the Liouville's theorem. So, but why? So where is the big difference? Why can complex differentiable functions behave like this? And again, so the answer to me is hidden in linear algebra. So this is what differentiability for a function from R2 to R2 means. There is a linear map that approximates your function up to order 1. And this is, as I've mentioned many times in this course, is much stronger than existence of partial derivatives. So if you write f, f of xy is a number in R2, is a point in R2, so its first and second coordinates are separately functions of xy. These are real valued functions. So we can ask whether ux, uy, vx, vy exist. And then if they exist at some point, we can put them in a matrix, which gives us a linear map. But the point is that because you can write this function, this matrix down, doesn't mean that actually the function is differentiable and this matrix represents the derivative. The harsh example is a function that is 1 along, say, a collection of points that converge to 0, but not along a line. This function actually has directional derivative in every direction equal to 0. So partials in particular exist and are equal to 0, and the matrix that you form is just 0, 0, 0, 0. But this function is not even continuous because it's 0 everywhere and just equal to 1 on these points which converge to 0. That's kind of the extreme case of how existence of partial derivatives mean nothing for differentiability. So already here we see that we are beyond just existence of partial derivatives. But then the question comes to the point that, okay, so this linear function that I just wrote down, f of x, y equal to x and 0, because it's a linear function, actually the derivative exists at every point and is equal to the function f. So the question becomes, what more does it take for a C infinity function from R2 into R2 to be actually complex differentiable? And that was the first aim of the lecture notes here. So let's recall the definition of complex differentiability, that a function is differentiable if this fraction has a limit that is a complex number. I think part of the confusion or the apparent surprise with complex differentiable functions is that on face, this is exactly how you define the derivative of a function from R1 to R1. But that is an unfortunate analogy. This differentiability, this fraction for R1 functions has nothing to do with this two-dimensional version. This is saying that in all directions, in a uniform way, you approach the same limit. And that's very, very strong. And indeed, it's stronger than the previous definition. So here we already saw that the directional derivatives was not even enough to give that there is a linear map with this property. And for complex differentiability, we will see that you need even more. And that more is hidden here. So if your function, this proposition, if your function is complex differentiable, it's also Frechet differentiable. That means as a function from R2 to R2, it is differentiable. That means there is a linear map which approximates your function. And the proof is just manipulation of algebra. So this is supposed to be the derivative. That means this fraction minus this number will converge to 0. But then you multiply and divide by z minus z naught. You put it in the same fraction, and then you get this. So from assumption, this goes to 0. That means this goes to 0. And guess what? This is a linear map. So this is the linear map applied to z minus z naught, and where linear map is just multiplication by this number w. Therefore, we see that complex differentiability is stronger and it gives it. So then the question becomes, when is it sufficient? Or, which is paraphrasing my previous question, what more does it take? If a function from R2 to R2 has tried hard and given us this linear map, which approximates the function, what more does it take to actually have this fraction go to 0? The answer is, again, linear algebra. This happens only for certain linear maps. And the linear map, for example, f of x, y equal to x0 is a linear map that actually maps R2 into just the real line. And we will see that this is a linear map that doesn't meet the criteria for stronger property of complex differentiability. Okay, so I have to speed up a little bit. The main point is that when a function was complex differentiable, its derivative, the Frechet derivative, the linear map, had this special form that it was multiplication by a fixed complex number, here W. What is special about such linear maps? The linear maps that are given by multiplication by a complex number have these properties. From just properties of multiplication by complex numbers, the modulus of L applied to Z will be, L of Z is W times Z, so this will be W times Z. And W is independent of Z, is a fixed number, so it means that these linear maps from R2 to R2 have this property that all the vectors Z are scaled by the same amount in their size. The other one is that, well, W multiplying by Z is just rotating it by argument of Z. So that means all vectors are rotated by the same amount, which means the difference between two vectors, they may map to different values, but then the difference in the angle they make with, say, x-axis remains the same. So that means they also preserve angles. They scale the same way. And also, all of them are rotated counterclockwise. So if you go this way, then the image of L also travels this way. Also from this property, it follows that circles are mapped to circles. So these will become very important, and that's why we define them, say, to be conformal linear maps, angle-preserving linear maps. And then I go through this proof that actually every conformal map, which now conformality is defined for linear maps R2 to R2 with no reference to complex numbers. You just suppose you don't know anything about complex numbers and you ask, what are linear maps that have these properties C1, C2, C3 that scale the same way in all directions, preserve angles, preserve orientation? And the answer is that they are none other than those maps that are of this form, that they are not just linear, but also they are complex linear, which means the scalar can also be picked to be a complex number. And that is the link between geometry, linear algebra, and complex differentiable functions. A linear map, again, from R2 to R2, preserves angles and orientation if and only if it is actually of this form. And then there is another characterization that these also happen if and only if the matrix that represents that linear map has actually this form that these diagonals are equal and this is negation of the other one. So this is the second characterization. And what does this have to do with complex differentiability? Okay. The main theorem is that if you have a function from an open domain in the plane to the plane, and it is complex differentiable if and only if it is Frechet differentiable, that means it's in the real sense differentiable, and this linear map, which is its derivative, is actually conformal, or just the zero function. Which means, again, equivalently, that if and only if the linear map, that is its derivative, is actually of the form multiplication by the constant. So if the derivative has this form, then differentiability upgrades from real to complex differentiability. And that was my goal in this course, to tell you Now it's obvious why, for example, a function like f of z equal to z bar, despite being a simple linear function, is not complex differentiable anywhere, because it actually reverses the orientation. Or for example, why don't we have real valued complex functions? Because the derivative is supposed to rotate everything the same amount. And but if you had a real valued function, if you had a function defined on this domain and its range was always here, this would mean that the derivative in some direction sends the vector to 0 vector. But remember, we had this property that L of z was the same quantity times z for all vectors z. This would force a to be 0. That would mean that the derivative is actually 0. Therefore, the function is constant. So this explains to a great deal why, if you write a random function, there is very little chance that it will be complex differentiable. So write your favorite smooth function. That means each coordinate component is individually C infinity. What is the chance that this has actually a point of complex differentiability? Almost none, because the derivative, once you compute, must be of this unique form that it's actually C-linear, or the more surprising part, that it has all these geometric properties. And well, if you write a random linear map, there is no reason for that to hold it. So that's why it's actually very rare to come across a complex differentiable function. Finally, I relate all of these to Riemann-Cauchy equation. Another, remember, characterization that everyone learns is how to check if a function is actually complex differentiable is to write the derivatives, compute the partial derivatives, and check if they satisfy Cauchy-Riemann equation, and someone has to memorize what they were. To me, the problem was always, the way I learn math is, something has to have some meaning, and usually for me it's just a geometric meaning, and not an algebraic equation that to me seems just random, someone just pulled out of their back. And they said, okay, I have this function and I will call it differentiable if and only if the partials have this unique thing. And then that doesn't explain many other properties. For example, why can I not have a real valued function only? Or why do I have more differentiability and things like that? It seems, initially, my argument is that if you just give them the Cauchy-Riemann equation, it doesn't seem that it's too strong, or it really restricts the amount of functions that actually satisfy them. Of course, ultimately it does. Everything is equivalent. But to tell someone that for a function to be complex differentiable, you need the derivative to have to preserve angles, to scale them all the same way, and also keep the same orientation, then you're more likely to say, okay, yeah, these functions must be special, and I don't think any function, even if it's nice from the real valued point of view, will be like that. But if you just look at Cauchy-Riemann, I mean, so how, where? Why, for example, z bar isn't like that? I know it doesn't satisfy the Cauchy-Riemann, but what's wrong with that function, for example? Anyway, so long story short, this is the only part I will go into detail because I'm so excited about. So we had this result that, sorry, not this, that other than being equivalent to conformality and being C-linear, a map has these has this, I don't know why series doing stuff. What did I say? Nothing. Anyway, so we had this, that linear map has those geometric properties if and only if its matrix actually looks like this. When you translate this, or rather you combine it with this theorem. A function is complex differentiable if and only if its derivative is conformal, has the geometric properties, but then that means its matrix is of that form. That means this are equal and these are negative of each other. So then finally we have this characterization that the function is complex differentiable if and only if we have the Cauchy-Riemann. So then we put all of this together and we have several characterizations. A few more characterizations of conformal linear maps are given here. So with that, I move into conformality, a section that was part of the syllabus. So I didn't have to cover the previous part. I could just say that you know what complex differentiability is from complex 1. And now we continue with this. But after doing all this hard work, maybe taking time to explain, to bring out the details about complex versus real differentiability, it was immediate such a theorem, and we didn't have to give really a proof that if you have a homeomorphism from one domain to another that is also complex differentiable, then it's a conformal map, which means its derivative locally preserves shapes. The precise definition is just saying that the derivative preserves angles. So it maps somewhere, and that is true at every point. And this we already know from previous section, that being complex differentiable implies that the derivative is angle and orientation preserved. We have to exclude the case of zero derivative. Anyway, so then I move into covering conformality and mentioning the Riemann mapping theorem, though the course wasn't too long enough to accommodate a proof of this. Then we talk about every possible conformal map from the disk to the disk itself. We use Schwarz lemma to identify all such maps, which is contained in this theorem. So every conformal map from disk to disk is of this form. And that motivates us to define Mobius transforms in more generality. So every creature of this type, modulo this condition, is called a Mobius transform, and then we define it on the Riemann sphere. One thing here that I'm kind of also happy with was I gave a precise definition of what Riemann sphere is, rather than the usual, okay, you have the stereographical projection, and then you put infinity here, and then this and that. Well, it's kind of convincing and geometric, but to prove stuff with this, you really need a definition. And I gave the definition through basically one-point compactification. So I defined open subsets of the Riemann sphere. So I say that Riemann sphere is this set plus a new element. So I can just define it. No one can stop me from adding some element to a set. But then to turn it into a topological space, I need to define open sets, which I do. The new ones are the complements of compact sets, basically. So complement of compact set, add infinity to it. These are neighborhoods of the infinity. And then I can rigorously prove, actually, that the Riemann sphere is homeomorphic to the actual sphere. And that is the stereographical projection. But now it's a theorem rather than the definition or hand-waving argument. And then we talk about some stuff, some with proof, some without proof, the behavior of Mobius transforms. And then I talk about some I call rigidity results. So previously we saw that every conformal map from disk to disk is of this form. But then also every conformal map of upper half plane to itself is of some form. That will be this. These we prove using just the Schwarz lemma for disk-to-disk maps. What we don't prove is, for example, all conformal transformations of C onto C are again Mobius transforms, but of course are the other special ones. and also all conformal transforms of the whole Riemann sphere to itself are also Mobius transforms. So we don't get into details of this. This wasn't part of the department syllabus, but once we were there, I wanted to continue with that. So that was 20 pages of stuff that we did in 2 weeks. That means 2 times 2 hours, so 8 hours of this. Because I started already with geometric properties of complex functions, I also wanted to continue with more. So we talked about this result that I mentioned, that open sets are always mapped to open sets, which is another way of proving that f of x, y equal to x is not a complex differentiable function, or any function that maps into a lower dimensional object cannot be complex differentiable because the image must contain an open set unless the function is constant. And okay, here there is a very important result that is needed, and that we postpone to the next section because we don't have the machinery to prove it. That basically says that you can factor out as many zeros. I mean, so this function at z naught is 0. If the function is not constant, then there is some maximum k which can be removed. That means this side can be divided by that, and g is still holomorphic. So basically saying that if you have a function and this of course is 0, you can divide by z minus z naught and still have a holomorphic function. And maybe you divide by 2 and it's still a holomorphic function. In general, there will be a maximal k you can do this with. And for k plus 1, it won't anymore be holomorphic. This is also very different from real differentiable functions. For example, this function from R1 to R1 is differentiable at 0. But if you take 1 power of x from it, then it becomes this, which is no longer differentiable. Okay, and then open sets and such. The rest is kind of more algebraic, analytic properties of complex differentiable functions. First, the global Cauchy theorem without simply connected domains, or well, without convex domains, say. So we talk about winding number, and also the question of when you have this integral equal to 0 for all holomorphic functions. If you have a domain U and you have a path, a curve in it, when is this integral always 0 for every holomorphic function of U you take? And the answer is when this curve is null homologous. It's different from homotopy. Okay, and then we have when is that integral always 0? No matter what path inside U you take, and no matter what function. What if also this is variable in this? And the answer is that it happens only if U is a simply connected domain. Okay, and after that, there comes the part where the most important maybe property of complex functions, in the sense that every other property you can deduce from this. If you have this, you can prove that they are infinitely often differentiable. If you have this, you can prove the lemma that I mentioned was crucial for the open mapping theorem, and many more. So basically, if you have this, you have everything. And that is, we can write every complex function as a convergent infinite sum. Basically, it's Taylor series. To prove that, we have to talk about uniform convergence in an infinity norm. And once we do that, we have some properties, consequences of uniform convergence. If fj's converge to f uniformly, then this integral converges to that. And once we have these, we can, I've been very careful. That's why these are many pages with every detail about uniform convergence and things. Here's the theorem that if you are holomorphic function on an open set and you take any ball, so the only restriction is that the ball needs to be contained inside U. So there is no restriction on how large this radius can be where function is equal to the sum. The only restriction is just the trivial restriction that it has to be inside the domain. Then the function, the series converges uniformly on that ball, and if actually equals the limit of that. So that is the main property of complex functions that I mentioned. And the proof of this is easy once you have the Cauchy's integral formula. So Cauchy's integral formula is amazing in that it gives the value of a function at z in terms of values of the function away from z. So this is a curve that wraps around z but is away from z, and because it's compact, it's actually a safe distance from z. And then notice that here z only appears in the denominator, so you have just 1 over c minus z, and which you can write like this, and then we have the famous summation that summation of z to power I is 1 over 1 minus z. And from that and higher, the Cauchy's formula for integrals, it just follows. So that's why this is only a half-page proof, because of the fundamental result Cauchy's integral theorem, which was done in Calculus 1. Okay, fast forward some more behavior of this. From this analyticity of holomorphic functions, you can prove identity theorem that a point is isolated. If a point maps to some value, then no point around that point maps to the same value any longer. And from that, you can prove that if you have an accumulation point of pre-images of the same value, then the function actually has to be constant. Okay, so the last sections I haven't still completed. They will be the residue theorem and Lorentz series. Comment in the below what you think about such an approach to complex analysis, how controversial you find it. Also, I'll put a link to my own website where you can find updated versions of these notes. Thanks for keeping up so far, and have a great one.